Yeah, welcome back. I hit play. I don't know if this is going to be interesting or not. You know, listen to this. 5.1, what did we do? Oh, we learned how to do integration, right? Anti-differentiation. But these were indefinite integrals is what they were called. When we integrate these indefinite integrals, we get a plus c. We get some function, some antiderivative plus c. And anyway, there's a lot of cool concepts in there, especially acceleration, velocity, and position. There's some good stuff in there. But it was really just getting used to integration. So anyway, I want to help you there, but I'm just trying to outline some thoughts here for you. In 5.2, we did area under a curve, which seemed like an unrelated idea. We're adding up rectangles. It seemed unrelated to that. And we added up inscribed, circumscribed, middle scribed rectangles. And my homework wants you to do some of that. The homework problems I assigned in 5.2 ask you to do that. What also is in 5.2 that I didn't want to ask you to do was add up an infinite number of rectangles. It gets pretty darn tricky to try to do n rectangles and then take the limit as n goes to infinity. There's some of that in 5.2, but I didn't really assign those problems. So if you do the ones I assigned, you're adding up a finite number of rectangles and you're estimating the area under a curve. Okay? So what happens in 5.3? In 5.3, they explain to you that the area under a curve, watch this, the area under a curve, f of x, from A to B, this shaded area under a curve is an integral from A to B, which now we call a definite integral. But this is the idea in 5.3. Hey, an integral is area under a curve. The function you're integrating is the function whose area you're looking for under the curve. From a left bound to a right bound. That's why I kind of, back in 5.2, I didn't want you to work too hard because, well, you had to add up some rectangles. But I didn't want you to do infinite number of rectangles. It's a real difficult process, and after you try doing it, the result is you just do this anyway. So this is area under a curve, or it can be interpreted as area under a curve. Look, those are the little widths of my rectangles. Those are the little heights of my rectangles. When you multiply them, it's area. This integral symbol technically is sort of a summation symbol, sort of. There's a lot of sort ofs going on here. I mean, when you add up an infinite number of rectangles, this is what you're kind of doing. That wasn't proven to you exactly, but it was told to you. But what's funny in 5.3, if you do some homework in 5.3, is there's a lot of visuals. What they want is they give you a picture and say, can you represent this with an integral? And then you do. Okay, this is the or they give you an integral. What picture does this represent? And then you sketch a picture of the function. So there's a lot of this back and forth. An integral represents area under a curve, and can you kind of do that? Now, the funny thing is, in 5.3, you don't know how to do this integral. Nobody taught you how to do what's called a definite integral. So finally, in 5.4, they teach you how to do a definite integral. And I did this too. I did it real quick, because I ran through these ideas last class pretty quickly. But I want to go back and digest these ideas. But let me just get to the point here. You can do a definite integral. It's called the fundamental theorem of calculus. I'm just going to write that here. The fundamental theorem of calculus. And here it is, a little more clearly maybe than I did the other day. If you're trying to do an integral with bounds on it, it's called a definite integral. Called a definite integral. So what you do is you do the antiderivative. The antiderivative, just kind of in general or abstractly here, we call it capital F of x. So you do the antiderivative, and then we put this little evaluation bar here. We evaluate from a to b. So you don't put a plus c on these definite integrals. You don't need the plus c. Instead, you're evaluating from a to b, and then what that means is you plug b into the antiderivative, plugging a into the antiderivative. And this concept of how to evaluate a definite integral is the fundamental theorem of calculus. There's actually a second fundamental theorem of calculus that I'm not as interested in. So if it comes up, we'll get there. But I don't know. I mean, to me that flows, but I tried to make it flow when I presented this the other day. I started here and I kind of ended up here quickly. Like I said, we need to go back and digest that. Think about and do some homework, I suppose. You should. And I can too, I guess. The next thing is 5-5. 5-5 is, I won't do today, I guess. Like I said, I want to go digest this. But it gets good. It starts to get good kind of quick. We have to do we learn how to do some substitution techniques and some stuff. You know, just another general vague statement here. You know, when you guys learn derivatives, you learned product rules, quotient rules, chain rules. You learned all the trig rules. You learned the inverse trig rules. You learned how to do an e function, a log function. You know what? You can do the derivative of everything. You can do the derivative of everything. There's nothing, now that you know all those rules, there's nothing I can make up any kind of terrible crap, and it would be a quotient rule within a product rule with some, I mean, you can do it. Doing antiderivatives is different. You can't integrate everything. So the stuff that's in the homework is set up for us to do. There's plenty of stuff. If you just walked up and made up some function, you might not be able to integrate it. There's no by hand method of integrating it. And if you can't integrate it by hand, and you can't find its antiderivative, and you can't do this, then you know what you might end up doing? There might be some value to, if I can't do this, then there might be some value to doing about 4 or 5 rectangles and estimating the area under a curve. That might be my best option to do something, because I can't physically do some antiderivatives. So there is value to some of this numerical technique of adding up rectangles. Usually I'm trying to teach you how to integrate, so we do stuff we know how to do. Anyway, if we jump back to 5-1, did you try any homework problems? Do you have any requests or anything in 5-1 that's I should help you with? And you can say, no, I'm an expert. I'm an expert. I don't have any questions for you. I don't even know why I'm sitting here. You could say that. No, you're not saying that. Okay, all right. You don't have to say that.
19.
Yeah, I thought about that one. Good. Hey, he just asked me for 19. And he's in 5-1. X plus 6 over the square root of x. Right, so when did I do this? I did it last Monday. I taught you how to do some of these things. And then Wednesday I went off into this new stuff. So we haven't digested this much, but I'll help you. You know, one thing with antiderivatives and integrals, we don't have, listen to this, there is no such thing as a product rule. There is no such thing as a quotient rule. There is, that's one important concept about integration. There is no product rules and quotient rules. What there is there's only kind of one rule. I sort of said it. It's that power rule. Like you can do x to a power. So you often have to manipulate what you're trying to integrate. You have to manipulate it a little bit to get it in a form that you can do. So I know what to do with this one. Bust it up or split it apart, right? And you got a numerator, several terms in the numerator. They all have a common denominator. If you split it up, you'll have separate terms that you can integrate, I think. So right, you should think of it as x over the square root of x plus 6 over the square root of x. Now let me do a little more rewriting. So what is that? That's an x to the first over an x to the half. When you combine, add exponents or subtract exponents, I think you end up with x to the half. Do you agree?
Yeah.
And over here, the 6 stays up there, but I think I'll move him up and call him x to the negative a half. So see, I've transformed the way that original thing looked by simply splitting it up, splitting up the numerator and doing a little algebra. And now I can integrate, but let me just pause. You guys okay with the algebra there? Splitting it up, doing some algebra. This is, yeah, you can handle this algebra. Now, let's integrate. The new rule of integration last week was the power rule backwards, the old power rule for derivatives backwards, which is now the power rule for antiderivatives, which is add 1 to the power and divide by the new power. And then instead of dividing by 3/2, I'm going to go ahead and do one little step called multiply by 2/3. Dividing by 3/2 is multiplying by 2/3. So I just went ahead and did that. Add 1 to the power, divide by the new power. That's it. That's the new game. Let's move over here. You got a 6. You leave the 6 there, and you integrate this little guy. You add 1 to the power. That's going to be x to the half. You're going to divide by a half. Dividing by a half is multiplying by 2. So we're multiplying by 2. Plus c. And we're done. We're done. We're finished. I like cleaning things up a little bit. Let me, not really. To tell you the truth, I'll give you another truth here. I'm done. I'm calling this done. Finished. Hey, when we did practice the heck out of our derivatives, wasn't it real important for us to clean up our derivatives? Didn't I focus on that a lot? Right. We had to clean them up. We had to factor out. We wanted them clean. The reason we wanted our derivatives clean is because the next step usually was, when does this derivative equal 0? When is this, I mean, we had to use our derivatives to talk about mins and maxes. Anyway, so we're just practicing antiderivatives now. And at the end of an antiderivative or an integral, I'm not a big fan of working on cleaning this up. I mean, you do a little minor cleaning, but you don't have to, there's no reason to work too hard here at the end. But the book might. The book might. So you do what you want to do. Look up the answer in the back of the book, and you may have to do some algebra to get from your answer to their answer, because they'll do some cleaning that I call a little unnecessary. But I'm happy with this. But they might do a little factoring out. They might do a little cleaning, but I'm happy with this.
No, that was the answer.
Okay, good. Good. What else? Any other cool requests? This is easy, but you have to split it up and integrate each separate term, and these are basic little power rules, and I mean, you gotta get good at this. Yes, ma'am.
Number 21 in 5.1, I got the answer, and I figured it out, but I got, in the final answer, it was a negative and not a positive, and I couldn't figure out why.
Okay.
For the answer.
So 21.
Mm-hmm.
So 21 is this integral x plus 1 times 3x minus 2 dx. Like I kind of just said, I referred to this one. I said we don't have product rules and quotient rules, so we didn't have a quotient rule to attack that, and I attacked it a different way. I don't have product rules for integration. I don't have that thing, so I probably should FOIL this out and integrate, I guess. So so that would be a 3x squared, a negative 2x, a positive 3x will be a positive x, a negative 2. So that's what I got. I mean, you might have just made a simple algebra mistake, but here we go. If maybe you didn't, maybe you're here, and if you're here, then you're correct. Now integrate each term.
No, that's exactly what I did.
You did something wrong, right?
Yeah.
When you FOILed, you just made a
I left it as
a negative
3x
x.
squared minus x.
Yeah, yeah.
That's exactly where it is. Thank you.
But you follow me, right?
Oh yeah.
Because I think it was
Yeah.
it was a positive 3x
Yeah.
and a negative. Yeah.
Yeah.
Yeah, that's all. Let's finish it.
Yeah.
For the rest of the crowd here. Okay. Add 1 to this. And then divide by 3, and when you divide by 3, it kills that 3, if you don't mind. X squared over 2, is that, you know, you can say it two ways. I go back and forth. I can say x squared over 2, or I can say 1/2 x squared. Hopefully you're smart enough to know they're the same thing. Yeah. And finally, how do you integrate a 2?
2x.
2x, that's right. Plus c at the end, and we're done. This is fine. Yep, cool. The antiderivative. Like I said, I'll say this one more time. You'll never see, I never do this though, but, and you probably don't either, but when you do these antiderivatives, you can always check them. How do you check them? At the end, do a derivative, and you should get back to the, I mean, if I took this guy's derivative, I would be here. If I took this one's derivative, if I did his derivative, I would probably be here. You know, I mean, you know, there's, in between here and here was a bunch of algebra, you know, but you can sort of check yourself if you might want to do a derivative at the end. Any other good requests?
Can you do number 10?
Number 10, yeah. The integral of 1 over 3x squared dx. Yeah, that's a good one. Number 10. The integral of 1 over 3x squared dx. And they kind of had these directions that said, they got these in the book there, rewrite this. And that's definitely, I mean, that's what you got to do. You know, like this one kind of. I had to rewrite this. I had to manipulate it and rewrite it before I could integrate. Same with this one. I had to FOIL it out and then I could integrate. Well, on this one, I think I better do some algebra here. What is this? It's a 9x squared, isn't it? And then to do a power rule, you got to move the x squared up. I'm going to think of this now as a 1/9 x to the negative 2. I mean, if you move the x up, you don't move the 9 up. I mean, the exponent is on the x, not on the 9. Now that I've squared everything, the exponent is on the x. You move it up. And now I'm ready to finally integrate. See, so there's 2 or 3 steps there of just algebra. Cleaning up, working on your manipulating the integrand. This is called the integrand. Before you finally integrate. Now I'll integrate. You add 1 to the power. So that's x to the negative 1. When you add 1. And then you divide by that new power. So you're dividing by a negative 1. There's a 1/9 out front, and then it's plus c, and this problem's over. Although it looks kind of like crap. So it should be cleaned up a little. I would, let's see. Basically, can't you just call this a negative sign? I'm going to just pull this negative sign out front here. Negative 1/9, and then what about this x? Just move him into the denominator? Just move him into the denominator. He's a 1 over x with a negative sign out front. Plus c. Sometimes the algebra is the hard part, you know. I mean, the calculus step was right here. And then it's the algebra to kind of make it look better. What else? Any other good requests? In 5.1, let's focus on 5.1. There's some, I like these questions. These are test questions. There's a little 35 through 41. There's a little batch of these. Here, let me try 42 with you. 42. They give me f double prime of x. It is 2 over x squared. They give me f prime of 1 equals 4. This is a piece of information here. And then they give me another piece of information. F of 1 equals 3. F of 1 equals 3. What's the question? The question is, find the particular solution that satisfies the differential equation and the initial condition. Wow, those directions could confuse you. I think I would word it a little differently. They called this a differential equation and they said to solve it. They're not wrong, but I haven't talked like that much. I think I would say this. But this is what, by the way, solving a differential equation means this. It means find the function f of x. So you're given a second derivative and you're trying to find the function. That's all. And if you're at a second derivative and you're trying to find a function, you probably ought to integrate, right? And when you integrate from a second derivative, you'll integrate one time and you'll get to a first derivative. And it'll have a plus c on it though, you know? I think this information here is supposed to help me find the plus c. Anyway, then I'll integrate again. I'll repeat that process. I'll integrate again to get to the function. And it'll have a plus c on it, a different plus c on it. I think this information here will help me find that plus c. Okay, cool. So I sort of outlined what I want to do. Let's do it. I'm saying to get to the function, I should integrate this second derivative. All right? I'm integrating this second derivative. You know, here I am again. I got to rewrite it. I got to move it up. I got to call it 2x to the negative 2. I got to add 1 to it. When you add 1 to it, you get x to the negative 1. Divide by a negative 1. That's how you do it. The 2 is multiplied out front plus c. Now, what should I call this answer? I just integrated f double prime. What should I call this?
F prime.
I should call it f prime. Thank you. I'm going to do that so I'm clear here.
Set it equal to 4.
Well, you're exactly right. Let me clean it just a tad here, but then you're right. Hang on just a minute. What do I want to do this? Can I call this I hate... So I never leave negative signs in the denominator too much, so you always see me move them up. So it's a negative 2 over an x. Is that what that is? A negative 2 over an x plus c. And this piece of information that's up here will help me find c. Look what it says. It says this. Now, what does that say? That says, in the derivative, f prime, if you plug in a 1 for x, the value of the derivative is 4. Says a lot, doesn't it, in one little. If you plug in an x into the derivative, if you plug x equals 1 into the derivative, the value of the derivative is 4. So let me try that. The value of this derivative will be a 4. What am I plugging in for x?
1.
A 1. And look what that does. That helps me find c.
Yeah.
I mean, I can find c. Yeah, that's a negative 2 added to the other side. C is 6. All right, hold on. Time out. We have to repeat that exact game one more time. Because what that game just did was it took me from the second derivative to the first derivative. What I have here now is the first derivative. What is it? It's negative 2 over x plus 6. And if I want to get to the function, then I think I should integrate this. Do you guys agree? So now I got to repeat the game one more time to get to the function. All right, this is a good one now. How do you guys know how to integrate him?
If you write negative 2 times 1 over x plus 6, then you can do the natural log.
All right.
Negative
So
2.
this is a negative 2 over x. We're all kind of new at this, but this is a famous, he's a 1 over x, if you think of him as a 1 over x with the 2 out of the, pull the 2 out of the way. So he's a 1, so 1 over x is a famous derivative of somebody. What was 1 over x was the derivative of ln of x. So if I'm going backwards and doing an antiderivative, the antiderivative of the 1 over x is the ln of x. So this is negative 2 ln of x. By the way, I'm supposed to put absolute value when I do that.
Yeah. Yeah.
Now that might feel like that's coming out of thin air, but it's not out of thin air. It's, if you remember his derivative was this. So his antiderivative is this. What about the 6? How do you integrate the 6?
6x.
6x. Thank you very much. That's how you integrate a 6. And then a plus c. Cool. This is my function. And it's my function, and it's got a plus c in it. The directions wanted what they called a particular answer. And that's because they gave me a piece of information right here that I can use to find C. Plug this in and you can find C. What it says is when x is 1, the function is 3. Okay? This is a 3. When x is a 1, you can find C. Turns out the ln of 1 is 0, so that's a 0, that's a 6. If I subtract 6, this is a negative 3. I think that's my C.
Right.
So I played this game twice. Starting with the second derivative, I got the first derivative, found its C, integrate that, get the function, find its C, and I'm done. That's a good little exercise. The final answer is the function, which is this with the negative 3 plugged in there. I'll just do it like this. That's good. That's good stuff. I like that. We do that with some good word problems later in this section. You can start with acceleration, and when you integrate, you get a velocity equation. And you know what? When you do that, there'll be a plus C on your velocity equation. Do you remember what the plus C always is in the velocity equation?
Initial.
It's the initial velocity. It turns out the plus C is going to be a V0. Hey, then you'll integrate a velocity equation and you'll get a position equation. S equals like negative 16 t squared, blah, blah, blah. And anyway, there'll be a plus C, and that'll be the S0, the initial height, or the initial position. So, I mean, here it was, abstract for any function, but the same game with an acceleration, a velocity, and a position, you can play the same game. I mean, we need to, toward the end of 5.1, there's some good word problems like that. There's some other good word problems that aren't acceleration. There's a 51 and a 52 that are good. I'm sorry. I finished this problem and I wanted to make a comment about something. So when you integrate this, it was the log of x. You guys are all convinced of that?
Right.
Okay. Here's the thing. If you thought for a second, a few minutes ago, when I did this, this wasn't a log. Look at this one.
No.
This wasn't a log. This was move it up and do a power rule. So move it up and do a power rule doesn't work when it's x to the first. And I think I showed you that, but let me just remind you. See, this was move it up, do a power rule. That's what this is. That's what this is. But when it's x to the first, you can't do that. Let me remind you, if you tried to move it up, it's called x to the negative 1. If you add 1 to that, you get x to the 0. There's really nothing wrong with that, except then you try to divide by 0. That, good. So you can't do the power rule for an x to the first in the denominator. Right. So an x to the first in the denominator is a natural log, by the way, actually. Right. If we remember that derivative rule. So he fails the power rule, and he's got his own special rule. He's a natural log. Right. All right, cool. I said that once. 52, yeah, I think so. It says the rate of growth of a population of bacteria is proportional to the square root of t. Now, what might be cool is if they made me write that mathematically, but what they did after they wrote that English sentence, they went ahead and wrote a mathematical sentence. They said that the rate of growth, and what do they call the rate of growth of a population? They call the rate of growth of a population dp dt. That's the rate of growth of a population. The derivative is a rate. The derivative is a rate of change. So the rate of growth is dp dt. They said it was proportional to the square root of t. So they wrote it's proportional to the square root of t. So the variables are here are p, which is population, and of course t, which is time, and this k is just some constant. By the way, it's not the plus c constant. It's just some constant of proportionality. I think they said this was proportional to this, so there's this constant k here. All right, let's see what else they say here. P is the population, T is the time in days. This is a population of bacteria. The initial size of the population is 500. Look, I'm going to write some stuff down. The initial size of the population. I think that means when T is 0, the population is 500. That's what they just told me, I think. See what else they tell me. After 1 day, the population is 600. Let me write that down. After 1 day, the population is 600. Population of bacteria. T is days. What's the question now? Estimate the population after 7 days. Okay, so now they want the population after 7 days. I read all that stuff and then I write down my information. You know, I'm a good little problem solver. I write down what they told me. I write down what they're asking. And look what, you know, they're asking me about population. And I don't have a population equation. What I have is this equation, which is the rate of growth of the population. What I have is the derivative of the population. I wish I had a population equation. If I got a derivative and I want to get to the original function, what should I do? Integrate, of course. Right? Okay, so I need to integrate before I can really do any solving. You know what I mean? Before I can do it, I need to integrate. All right, so I think I'll integrate. You know, I mean, I don't want to complicate things. I simply want to integrate this. K is a constant. I simply want to integrate t to the 1/2. But just for the purposes of a little teeny notation talk here, it's kind of like you multiply the dt over here. This is just a different way of talking maybe. Watch this. And then you integrate both sides. And on this side, you're integrating a 1 with respect to p. So you're integrating with respect to the variable p, and you're integrating a number 1. What's the integral of a 1?
P.
A p.
Oh, a P. Yeah.
Right, on this side. Anyway, we get our population equation is what we're getting here. When we integrate dp, we get p. On the other side, I'm integrating with respect to t. K is a constant. I'm going to hold the k there. It is a t to the 1/2, so I think I'll call it, I'm going to do it. I think I'm going to do it. T to the 3/2 times 2/3. I think that's how you do him, right? Integrate him. He's a t to the 1/2, and I did it. Plus c. Cool. That didn't take too long. I integrated. I mean, I moved this dt over and I integrated both sides. I mean, that's a nice way to talk. You could have just said, I'm integrating this. And you would have got this. And call it p. All right, so now what? You know, they want the population when t is 7. So I can plug in my 7. The problem is I got a bunch of unknown constants. I don't know c and I don't know k. Well, that's what this other information is for. I bet you if I started plugging in some of this other information right here, I bet you I could find C and find K. That's what all this is for. Plug this stuff in, you'll find C, you'll find K, and then you can answer the question. Now, you know what? I'm just going to do my 2-minute pause. If you want to work on that, you can. And I'll be right back to help you finish it.